With this lesson, I want to give you guys a little bit better idea of what's going on in your reading in section 7.6. Let's just start with something we're familiar with, a system of two equations. You learned how to solve these. You've been solving these kinds of things for a long time, really. But I've got these two lines, x1 plus x2 equals 3, negative x1 plus x2 equals 1. If I want to solve this system of equations, we know what this means. We want to find where do these two lines intersect. Now, if I drew them carefully enough, you can kind of tell just by looking what the solution is going to be. But we don't want to tell by looking. We want to actually do the math. And if you do the math, this system is solving this system is the same thing as setting up this matrix equation, ax equals b. Where we've got a, and then our x vector, and then our b vector, right? So if we solve this, you've learned all kinds of ways to solve this, but if we solve this using Gaussian elimination or inverse matrix or whatever method you want to use, or going back even further, you can just do like an elimination method or a substitution method. We are going to get the vector 1, 2. All right, which is exactly what it looks like, this point 1, 2. So if x1 is 1 and x2 is 2, then that is the point that satisfies both equations simultaneously. Now, what we're dealing with in 7.6 is we're dealing with scenarios where you have more equations than you have unknowns. So here we had two equations with two unknowns. Let's look at what they mean when we say that we have more equations than there are unknowns. So here I have three equations with two unknowns. All right, it's the same system that we had on the previous slide. I just threw in one extra equation, x1 plus 3x2 equals 3. And now all of a sudden, if we ask you to solve this system of equations, there's not a solution. There's not a single point x1, x2 that satisfies all three equations at the same time. So if we want to solve this thing, the best we can do is come up with an approximation to a solution. So in a perfect world, if we had a solution, then when we do b minus ax, if we had some vector x that worked perfectly, then this would come out to 0. But we don't have a vector x that works perfectly here, that works in all three equations at the same time. So the best we can do is we can take this b minus ax and make it as small as possible. All right, so this is kind of the goal of our least squares problem. The idea of the methods that they talk about is, let's take the norm of this vector, and specifically they use the 2 norm. Let's take the norm of this vector and find some way to make it as small as possible. All right, so we want to make this as small as possible because we can't have it being 0 because there's not a solution. So let's just make this as small as we can. And they talk about two different ways to do this, but just before we get into those, again, just graphically what's going on is, let's say we just tried to randomly pick a spot that is a good solution. So like if I picked this point right here, 1, 2, that worked with the previous system, well, that's fine. That point is really close to the first two lines. It's actually on both of those lines, but it's not that close to the purple line. All right, so maybe that's not the best choice. similarly, I can pick like maybe this point over here. That works great for lines 1 and 3 because it's on both of them, but it's pretty far away from that second line. So whenever we talk about making this residual, this vector here is called the residual. This thing that we're taking the norm of. When we talk about making this residual norm as small as possible, we're finding basically the thing that kind of comes as close as possible to satisfying all three. So it's as close as possible to all three lines, but maybe it's not actually touching any of them. So graphically, you can maybe kind of look at this and see that maybe somewhere around here would be our best bet, because right around there, it's not too far from any one of my three lines. It's not touching any of the three lines, but it's better than, say this point over here. That's it's going to make two of my lines satisfied, but the other one, it's not even close. So if I did the norm of my residual out here at this point, I'm going to get a much larger norm, or the size of that vector will be much larger than if I moved over here where I'm relatively close to all three lines without touching any of them. All right, so that's what our methods are really all about in 7.6, is finding the best fit. There's not a solution, so let's find something that's as close as possible. All right, so in the next slides, I'll just kind of run through the two main ways that they talk about finding this least squares solution. So two ways that they talk about solving systems like what we had on the previous page. One is what's called normal equations. The other is QR decomposition. The normal equation approach is pretty straightforward. You take this system AX equals B, like what we had on the previous slide, where there's no real solution. There's not a solution to the system. There's not some vector x that works in all the equations at the same time. But they actually show a proof in the book that if you multiply this equation on the left, on both sides on the left by A transpose, then solving this system, A transpose AX equals A transpose B, is guaranteed to minimize that residual norm that we were talking about, that norm of the vector B minus AX. B minus AX is not going to be 0 because we don't have an actual solution to the system, but they prove in the book that solving this system, this normal equation, will minimize that residual norm for us. The other way that they talk about is called QR factorization, and we've talked about factoring, or QR decomposition. We've talked about factoring A before. We did the LU factorization. QR is just another approach, a different way of factoring A. We factor it in a way so that that matrix Q forms an orthonormal basis for the space spanned by the columns of A. And I know there's a whole lot of linear algebra lingo in that one sentence. Don't worry too much about it. You can try to sort through that. Think back, maybe look up some definitions and try to remember what all these words mean. But the main idea is whatever this factorization QR is, if I replace A with Q times R, since the columns of Q form an orthonormal basis, if I do Q transpose times Q, I'm guaranteed to get the identity matrix. So then multiplying this QRX equals B on the left by Q transpose, the Q transpose and Q will cancel and leave you with just R times X. And then on the right, you'll have Q transpose times B. And here R is an upper triangular matrix, which is nice because we've already talked about how solving systems with a triangular matrix is easy. It can be done in fewer steps than a regular matrix. All right, so again, they go through the description in the book, and hopefully you read that and try to make sense out of that. And again, please feel free to reach out to me if that doesn't make sense. But they go through the proof in the book explaining why solving this system, Rx equals Q transpose B, is guaranteed to minimize our residual norm. All right, so whether we use the normal equation or the QR decomposition, either approach will give us the same answer. It'll give us the answer that minimizes that residual norm for us. So if we've got two approaches that give us the same answer, and again in the book they do the same example twice using the two methods, and if you look at those two examples, you'll see that in the end they got the same answer twice, right? So both methods do the same thing. So then the question is, why would we choose one over the other? Anytime we have in math where we have multiple approaches, there's probably some pros and cons to each one. So just to kind of summarize what they say in the book for you, the advantage to using the normal equation is that if you're solving some small system like the one we had on the previous slide, if you're doing this by hand, then it's pretty easy to multiply both sides by A transpose and then solve that system. It's for a small system, it's nice and easy to do by hand. The problem with the normal equation, they explain this down at the bottom of page 167 in your book. If you want to talk about how well conditioned this equation is, for the condition number, we need to do the norm of A transpose A, and we need the norm of A transpose A inverse. And here we're talking about the 2 norm. So if we want to find the condition number for this system, we need to find these 2 matrix norms, and it turns out that the norm of A transpose A is equal to the norm of A squared. The norm of A squared. So if A is any matrix that has a large norm, then A transpose A, the norm of that will be even bigger. And similarly, A transpose A inverse is going to have, it's going to be equal to the norm of A inverse squared. So if A inverse is a matrix that has a large norm, then A transpose A inverse will have an even bigger norm. So if either of these numbers, the 2 norm for A or the 2 norm for A inverse, if either of those are big, then your condition number for this system will be a big number. So it's really easy to end up with a large condition number. We have a large condition number. If our 2 norm of A is large, or our 2 norm for A inverse is large. All right, so that gives us a problem because we know that if we have a large condition number, then maybe small round off error or small changes will result in a big overall impact to our answer. And so if we're dealing with this on a computer, doing it by hand we may not have an issue, but if we're dealing with some large system on a computer, then the poor condition number could throw off our answers quite a bit. And actually in your homework, question I believe 14, they have you do this both of these ways. They have you do it with the normal equation, and they have you do it with QR decomposition. The nice thing is that they just show you the commands that you type into MATLAB, and it'll spit out the answers for you. And if you do it correctly, I expect that your answer that you get using the normal equation will be pretty far off from the actual answer, because you're going to be dealing with a whole lot of rounding. And if you're dealing with rounding and a poor condition number or a large condition number, then you're going to run into problems. Okay. On the other hand, the QR decomposition, you're not going to run into those same kinds of issues, and QR decomposition is typically what will be used in practice. The drawback to this approach is finding this matrix Q. If you're doing this by hand, finding that matrix Q is pretty troublesome. You have to go through this whole procedure for getting this orthonormal basis called the Gram-Schmidt algorithm, which maybe you saw in linear algebra, maybe not, depending on who is teaching it. But doing this by hand is pretty ugly. You don't want to, ideally you don't want to do this QR decomposition by hand, but fortunately, again, computers can do this pretty nicely for us. They can come up with this decomposition, and actually they don't use Gram-Schmidt. They have some other way of handling it. But in MATLAB, if you have some system where there's more equations than unknowns, like we saw on the previous slide, and you ask it to solve ax equals b, so you do the command a/b, MATLAB uses this approach. Basically, a QR decomposition is how it'll come up with its best approximation to a solution. All right, so the QR decomposition is best if you're doing things in a computer. If you're doing a small system by hand without a computer, then normal equations is probably preferred. All right, so take a look at your homework, those last few questions, and work on those. And before you work on those, you're going to want to read section 763, especially for number 14 in your homework. Read section 763 carefully and try to make sense out of what's going on in those examples. And let me know if you run into any issues with those examples, because you'll need to understand those in order to do your last couple of homework questions. All right. But otherwise, this will be the end of chapter 7 notes. So your homework over this chapter will be due next Tuesday. So please email me or catch me on office hours or something if you run into any issues with that assignment.